Synthesis of tri-substituted benzenes. When a di-substituted benzene undergoes an electrophilic aromatic substitution reaction, the directing effects of both substituents have to be considered. If both substituents direct the incoming substituent to the same position, the product of the reaction is easily predicted. So here is one such example. Here is benzene molecule on which you have a methyl group and nitro group which are para to each other. And when you look into the directing effect of these groups, you can tell that this is an ortho and para director, whereas this is a meta director. But the meta director with respect to nitro group is going to be in this place, and the ortho director or ortho position with respect to methyl group is also in this position. But since the para position is already filled, there is no way that the electrophile can go and get attached here. So the only place that the incoming electrophile can go on here is going to be this position. So one of the nitro groups is going to go get attached right here. Okay, or it can also be here. Both are equivalent positions. Now let's go on to the next one. Here is a compound where you have a methyl group and a chloro group meta to each other. Now, let's identify what are the different effects of these groups. Okay, so a methyl group is an ortho and para director, and chloro group is also an ortho and para director. But the positions of these groups is going to be different. Okay. Now, but the directing effects of these groups are different. So now let's see what are the different products that you will be getting for this reaction. So when the methyl group has its effect, it's going to put the nitro group in the ortho position. So here are the ortho positions, and here is the para position. So we are going to fill these places with a electrophile. Okay, so that's my first product. And here is my second product. And this is my third product. Okay. Now, since a chloro group is also ortho and para directing, the ortho position with respect to chloro group is right here, which is exactly the same product as this. And the para product will be here. The para, when the electrophile goes onto this position, it will be right here, which is this product. So basically, these two products are exactly the same as what you would get for chlorine. Okay, but when you consider all these three different compounds that you get, this product right here is not going to be feasible at all, because that's going to put the electrophile in between the two groups, which is going to be sterically hindered. Okay, so the electrophile is not going to make its way onto this carbon. Okay, so these are the only two products that you'll be getting for this reaction. Okay, the synthesis of another example for the synthesis of tri-substituted benzenes. So here you have an OH and CH3. Now, OH is a strong electron donating group, electrons or strong activating group, whereas CH3 is a weakly activating group. But they both are ortho and para director. Okay, so ortho and para and ortho and para. Okay, so if the OH is going to have its effect, then it would be this position, ortho position. Since the para is already filled up, there is no way that the electrophile can go on here. But the methyl group is going to have its effect on its ortho position, which is right here. Now, which of these effects is going to predominate? The answer is going to depend on which one is going to have more activating effect. Obviously, it's going to be OH. So the incoming electrophile is going to go into one of these positions. So this would be the answer. Okay. Next example. Here you have two alkyl groups, but the two alkyl groups are different. Although they are different, they are going to have exactly the same effect. So here in this case, the methyl group, both the methyl groups are going to be ortho and para directing. Since they are, both the alkyl groups are para to each other, obviously both the para positions are occupied, and therefore they can only have ortho substituted products. Since they have equal effects on directing the electrophile, they will have equal amounts of products. Okay, so the ortho position with respect to methyl group is this, and the ortho position with respect to the ethyl group is right here. Okay, so you will get actually a mixture of two different compounds. Arene diazonium salts. The list of substituents that can be placed on a benzene ring can be expanded using arene diazonium salt. And here is the structure of arene diazonium salt, and here is the diazonium group. And because the nitrogen has a positive charge on it, there should always be some counter ion that exists along with it. Now, what's the use of this arene diazonium salt? Arene diazonium salts can react readily with a nucleophile, liberating off nitrogen, which is a very stable compound, which is a very stable gas. Okay, so it is always recommended that you prepare benzene diazonium chloride or benzene diazonium salt freshly when you do this reaction. Okay, how do we synthesize arene diazonium salt? Okay, when anilines are reacted with sodium nitrite in the presence of HCl at 0 degrees Celsius, it can produce nitrous acid in situ, and can give rise to the formation of arene diazonium salt. Okay, so remember that for this reaction, it has to take place at 0 degrees Celsius. Raising the temperature would destroy the arene diazonium salt because nitrogen can escape from the arene diazonium salt. Okay, what are the reactions that the arene diazonium salt can undergo? The main reaction is the Steinmeier reaction. Okay, for Steinmeier reaction, you will react the arene diazonium salt with the corresponding cuprous salt. Say, for example, if you want to put a bromine on a benzene molecule, then you will take cuprous bromide. But if you want to put a chloride on the benzene ring, you will take cuprous chloride. Okay, and putting the nitrile group, you'll take cuprous cyanide. So basically, this is the Steinmeier reaction, and in all of this, you can tell that the benzene diazonium chloride or the salt is actually destroyed to give the nitrogen gas. And remember, in Steinmeier reaction, we cannot use KCl or KBr. Okay, what is the advantage of Steinmeier reaction? Okay, so let's say that we want to prepare para-chloroethylbenzene. So if you want to chlorinate ethyl benzene, then under the normal electrophilic aromatic substitution reaction, basically halogenation, we know that an ethyl group, which is an alkyl group, is an ortho and para directed. So you will get a mixture of both ortho and para substituents. But if we do the Steinmeier reaction, we only get the para substituted product. So where you have the amino group in the para position, so you take a para ethyl aniline and then reacted at 0 degrees Celsius with nitrous acid, and you form the arene diazonium salt, and then later on it is reacted with the cuprous chloride to give the para substituted product, where this diazonium group is actually replaced by the chlorine. Okay, by using this method, you can also synthesize aryl fluorides and iodides, but this reaction would not be a Steinmeier reaction, because for Steinmeier reaction, you will always use the cuprous salt. Okay, so the source for iodine is going to be potassium iodide, where it's going to replace the diazonium group and put the iodine on the place where it was. Okay, and for for synthesizing the aryl fluorides, you will use fluoroboric acid. So this is boric acid, and this particular reaction is actually called a Schiemann reaction. So after the diazonium salt is formed, okay, you will heat up the reaction to get the fluorobenzene. Again, in all of these reactions, nitrogen is going to be liberated because that's the way that you can destroy the arene diazonium salt. Okay, and also phenols can also be made from arene diazonium salts. Okay, so when arene diazonium salts are heated in an acidic solution, then you get phenol. You can have the OH, which is a nucleophile that replaces the diazonium group. And suppose if you want to increase the amount of phenol, then you can actually use a mixture of copper 1 oxide and copper 2 nitrate. That's going to give an increased amount of the phenol. One important reaction with respect to arene diazonium salts is it can be the diazonium group can be replaced by a hydrogen. So let's look into this reaction. So this is aniline. Aniline, when it undergoes bromination with the catalyst, remember this is going to be, normally you don't require a catalyst for halogenation when you have a strong electron donating group. Okay, so this is going to brominate in all the vulnerable positions. So here there are 2 ortho positions and 1 para position. So the bromine is going to go in all the 3 different positions. And then when this undergoes the diazonium salt formation, it's going to put the diazonium group right there where the amino group was initially present. And then when it is reacted with hypophosphorus acid, this is hypophosphorus acid, it's going to put the hydrogen in there. Okay, so this is a very useful reaction where you can actually where the amino group is used for directing purposes. So it's impossible to it is difficult to envision how 1,3,5-tribromobenzene could be synthesized without this nucleophilic aromatic substitution reaction. So far, we have been talking about the electrophilic aromatic substitution reaction of benzene. What about nucleophilic aromatic substitution of benzene? Does benzene undergo nucleophilic aromatic substitution reaction? Usually, aryl halides do not undergo nucleophilic aromatic substitution reaction because, remember, in an SN1 or an SN2 reaction, the aryl halides do not undergo both SN1 and SN2 reaction. The reason is the nucleophile is actually repelled by the pi electrons in the case of SN2, and in the case of SN1, it's not going to form a carbocation. It's not possible for it to form a carbocation. So for these reasons, the aryl halides do not undergo nucleophilic substitution reactions. But in certain cases, there is a possibility that it can undergo nucleophilic aromatic substitution reaction. The condition is it needs to have an electron withdrawing group. And it needs to have the electron withdrawing group, particularly in the ortho or the para position. Okay, so now here are 3 examples. And now let's take the first compound. Here you have the leaving group. Cl is the leaving group, and you have the electron withdrawing group right here in the para position. Okay, and there is only 1 nitro group. 1 electron withdrawing group here. For this particular reaction to occur, you subject it to a very harsh condition where the pH is 14, which is like really basic, and the temperature is 160 degrees Celsius. Okay, so when the OH minus goes and attacks here, the Cl is going to leave, and it's actually, since the condition is basic, you will first form the this compound or this intermediate, and then later on when it is reacted with acid, it's going to get protonated and you will form the paranitrophenol. Okay, now let's go on to the next reaction. Here, instead of 1 nitro group, you have 2 nitro groups, which means the withdrawal effect is going to be more. Under such circumstances, you don't have to go on to such harsh conditions. Instead, the temperature has been decreased here to 100 degrees Celsius, and the pH is also decreased. Okay, so and we have the substituted product. And in the next case, where you have 3 nitro groups, the pH of this reaction is 7, which is neutral condition, and the temperature can be lowered to 40 degrees Celsius, and even in that temperature the reaction has gone to completion. So it is possible for substituted benzenes to undergo nucleophilic aromatic substitution reaction, provided they have strong electron withdrawing groups in the ortho or the para position. Okay, so here is the mechanism for the nucleophilic aromatic substitution reaction. So in the first case, the nucleophile will go and attack the carbon where the leaving group is present. Remember, it cannot do the backside attack here. Instead, the nucleophile attacks the carbon at the trajectory that is nearly perpendicular to that of the ring. Okay. And it's going to form a series of resonance contributors, which is basically called a Mason-Hehmer complex. And then in the next step, which is the fast step, the leaving group is going to leave as the electrons are going to come in and form the product. Now, why the electron withdrawing groups must be ortho or para to the site of attack? The most important thing is the electrons can be delocalized only onto the ortho and the para position. They cannot be delocalized onto the meta position. Say, for example, if I'm going to draw the structure here, okay, so let's draw the structure with the nitro group in the meta position. So as the nucleophile comes and attacks this carbon, these electrons will come here, but then it is these electrons that will be delocalized. It cannot go and get delocalized onto the nitrogen. So because of which you want the electron withdrawing groups on the ortho or in the para position. So only in the ortho and the para position can the electrons be delocalized. Okay, so next one, many nucleophiles can engage in nucleophilic aromatic substitution reactions. So say, for example, fluorine can be replaced by a methoxide ion, and in all of these cases you needed to think that this nucleophile should be relatively stronger than the one which is which should act as the leaving group. So again, here you have the amine. We know that the amine is a stronger base than the bromine. Okay, only then the reaction is going to happen. Okay, so here when you heat the amine with this compound right here, it's going to get converted into this intermediate, and then later on when reacting with a base, it's going to go grab this hydrogen, grab the hydrogen on the nitrogen, and it's going to form the product. And in all of these cases, the nucleophile must be a stronger base. Synthesis of cyclic compounds. Cyclic compounds are formed from an intramolecular reaction. So what is an intramolecular reaction? When the nucleophile and an electrophile is going to be present in the same compound, then it can undergo intramolecular reaction to form a cyclic structure. Okay, formation of 5 or 6 membered rings are generally favored. So here are 2 such examples. So in the first case, you have 2 intervening electrons, so 2 intervening carbons, and 3 other atoms which are taking part in the intramolecular reaction, giving rise to a 5-membered ring structure. And in the next example, you have 3 intervening carbons, and these are the 3 other atoms which are involved to form the 6-membered ring structure. Okay, through intramolecular reactions, you can prepare a variety of compounds. Here is the synthesis for cyclic esters. Now, how do we generally prepare ester? For ester, you need a carboxylic acid and an alcohol. But if these 2 functional groups are present in the same molecule, then you actually can prepare a cyclic ester. So here in this case, this is a nucleophile and here is the electrophile, and between these 2 you can see that there are 4 intervening carbons. So my first carbon, second, third, and fourth, And the two other atoms that are involved is the oxygen and the carbonyl carbon. So together there are 6 atoms, which is going to form a 6-membered ring structure. And similarly here, this ester is a 5-membered cyclic ester, which is formed from 3 intervening carbons and 2 other atoms. One is a carbonyl carbon and the other one is an oxygen. Okay, the synthesis of cyclic esters, ethers. So here is an example for synthesizing a cyclic ether. So here you have a nucleophile and a leaving group, and therefore this is going to be your electrophile. Okay, so sodium hydride is going to be the hydride donor, which is going to go grab the hydrogen from the alcohol or the hydroxy group, which is going to form a negatively charged oxygen. And it is this negatively charged oxygen which is going to be as a nucleophile attacking the electrophilic carbon, which has the leaving group. And so it goes and attacks this carbon and thrusts these electrons onto chlorine, which is the leaving group, and thereby forming the 5-membered ring structure. And why 5-membered ring structure? You can see that there are 3 intervening carbons, 1, 2, 3, and then 2 other atoms, which is actually forming the, actually you have 3 intervening carbons. Here are the 3 intervening carbons, and there are 2 other atoms. Okay, so basically 5 atoms which are involved in here, and therefore it's a 5-membered ring structure that's formed. And there is also another way to synthesize cyclic ether, which is through the electrophilic addition reaction of an alkene, which also has an hydroxy group on it. So reacting it with HCl will add the hydrogen onto this carbon, because that's the one which has the more number of hydrogens. So once the hydrogen is added onto this carbon, you will have the carbocation on the other carbon, and then the oxygen will act as a nucleophile attacking the carbocation. And it's again an intramolecular reaction where it's going to form a total of where it's going to form a 6-membered ring structure. Okay, and remember there is a total of 4 intervening atoms in there. So these are the 4 intervening carbons, and these are the 2 other atoms. So 4 plus 2 is going to be 6-membered ring structure. Okay, and after this, a base comes and abstracts this hydrogen and will form the ether. Okay, the biggest advantage with intramolecular reaction is the product obtained from an intramolecular reaction can undergo further reaction, making it possible to synthesize many different compounds. So here is one such example. So here is a compound which has a nucleophilic part and as well as an electrophilic part. This is Friedel-Crafts intramolecular Friedel-Crafts alkylation reaction. So where it's going to go and attack this carbon and thrust these electrons onto chlorine, making it a leaving group, and thereby forming this compound. This compound has an allylic carbon. So here is your allylic carbon, and which has 2 hydrogens on it. When it is reacted with N-bromosuccinimide, which is specifically used for allylic bromination, one of the hydrogen is going to be replaced by a bromine group. Now you can consider this is more like an alkyl halide. So remember all the different reactions of alkyl halide. So it can undergo elimination reaction, forming a double bond right there, or when you're going to react it with magnesium and ether, it can actually form a Grignard reagent. So once the Grignard reagent is synthesized, you can react it with the other different reactants to form some industrially useful compounds.